In today's lesson, we're going to look at how to solve exponential equations when the bases are different. So a few lessons ago, we looked at how to solve an exponential equation when you could convert them to the same base, something like that. But what happens if they have different bases? Then we would end up using logarithms. So we're going to try a few of these questions here. So this first one, I would actually probably just convert to logarithmic form, but in order to do that, I need to isolate my exponent here. So I'm going to divide that 2 over. Whatever you do, and sometimes I always have kids do this, you cannot multiply the coefficient into the base of the exponent. All right, so what we're going to do is we're going to isolate that exponent and we're going to divide the 2 over. So then we end up with 5 to the exponent of x minus 2 equals 50. And then we'll convert to logarithm form. So my log, my base is 5, my argument is 50, and it all equals my exponent, which is x minus 2. Okay, if I type log 550 in my calculator, I end up with 2.4306768 equals x minus 2. And then I can just add the 2 over, and I end up with 4.4. So for these questions, we're going to round to the nearest tenth. Now, we've talked about this plenty of times before. With this course, you want to verify whenever you can. So whenever we're solving, whether it's exponents, logs, trig functions, anything, and you have 2 sides of the equation, you can graph. So type this into y1, this into y2, find the intersection point, make sure it matches your answer here, and then you know for sure that you did it correctly. All right, so this next question, our exponents where we can't divide anything over, right? Each exponent is already isolated. The first question you always have to ask yourself, can you convert this so that they have the same base? So is there any way for me to write 6 so I have a base of 2? No. So then what my next step is I'm going to log both sides of the equation. So when we're working with equations, we always want to balance an equation out. So you could multiply 2 sides of an equation, right? As long as you multiply by the same number. You can also log 2 sides of an equation. So we're just going to log both sides. Okay, now that we've logged both sides, we use the log law. So if you remember, one of our log laws is when you have an exponent on the argument, you can move that forward as a coefficient on the log. So you could use really any log with any base for your log when you log both sides. I use just a common logarithm, which is a base of 10, just to make it easier to punch in my calculator and work with. And once again, I use my log law and bring that exponent forward as a coefficient. Okay, so now I'm just going to distribute. So I'm going to take that x times the log 2, and then the 3 times the log 2. So I have x log 2 plus 3 log 2 equals x log 6 minus log 6. Okay, and then I'll collect like terms. So I'm going to bring all of my x's to the same side of the equation, which means I'm going to move this x log 6 to the left. And you could go either way here. And then I'm going to move that 3 log 2 to the right. So then, of course, when I move something from one side of the equation to the other, the sign will change. Okay, so now that I'm at this stage, I'm going to factor that x out. Okay, now that I've factored that x out, in order to isolate the x variable, because that's what I'm trying to do when I solve, is I'll just divide this expression log 2 minus log 6 over to the other side. Okay, so you really don't need to simplify any further from this. Okay, so this would be my simplified answer, which, it doesn't look very simple. You could use log laws and try to continue simplifying, but I will just accept this as an acceptable answer. But the next step that you're going to try to do is you're going to try to type this in your calculator. So whenever you have a numerator that's more than one term, and a denominator that's more than one term, you want to make sure you use brackets. So I want you to go ahead and try typing this in your calculator, and you should end up with 3.52. So I'm actually, and I could have done this on the last question. The curly equal sign just means approximately. Let's round this one to the nearest hundredth. So my answer is 3.52. So try that on your calculator. Again, if this was a test, I would take the time, graph the left side, graph the right side, make sure my answer matches up. All right, next question. So again, we really need to make sure we drill this in our head. Whenever you look at a question, always ask yourself an exponential equation. Can you convert to the same base? Okay, so this next one, can I convert 8 and 4 so that they have the same base? Yes, so that's always what I'll do if it's an option. So 8 is the same as 2 with an exponent of 3. And sometimes I have kids who ask, well, could I still log both sides? You could, but you will find that I will give you more difficult questions where you can convert with the same base. So that's why you need to make sure that you recognize one or the other. 4 is 2 to the exponent of 2. Okay, now all I'm going to do is distribute that 3, so I end up with 9x plus 12 equals 2x minus 18. Great, so now I can cancel out the 2's, and I end up with 9x plus 12 equals 2x minus 18. Okay, and then I'm going to collect like terms and solve for x. So I'm going to subtract that 2x over, and I end up with 7x plus 12 equals negative 18. And then I'll go ahead and I will subtract the 12 over. Negative 18 minus 12 gives me negative 30, and then of course I'll divide that 7, and you end up with negative 30 over 7. Okay, or you could round this. If you wanted a decimal answer, you would end up with negative 4.3. Okay, and again, I double check that on my graphing calculator. Okay, next question. So again, can you write this so that they have the same base? So we have 3 and 1 over 5. Is there any way to write them so they have the same base? No, there's not. If I had 3 and 1 over 27 or 1 over 9, I could write that with a base of 3, but unfortunately, 3 and 1 over 5, there's nothing I can do there. So what we end up doing is we log both sides. Okay, so that's always our first step, log both sides. Then we use log laws. So here, my log law, I'm bringing that exponent forward. And over here, I'm bringing my exponent forward. Okay, and then I'm going to distribute that coefficient. So I end up with 2x log 3 plus log 3 equals x log 1/5 minus 3 log 1/5. Okay, and then I can bring my x's to the same side. So I'm going to go ahead and subtract this x log 1 over 5 over to the left. And then on the right, I will subtract the log 3. Excellent. Now I'm going to factor out an x here, and I end up with 2 log 3 minus log 1/5 equals negative 3 log 1/5 minus log 3. And then I'll just go ahead and divide that expression over. So then my answer is x equals negative 3 log 1/5 minus log 3 all over 2 log 3 minus log 1/5. Practice typing this in your calculator. You'd be surprised how many kids I have do all the right work and then they don't type it in their calculator correctly. Make sure you put brackets around the numerator and denominator. If we type that in our calculator, we should end up with x is approximately 0.98. And again, this is a perfect example of something I double check graphing. All right, So now we're moving into a bit of a problem-solving type question. So the population of a particular town on July 1st, 2011 was 20,000. If the population decreases, so I'm going to underline decreases, at an average annual rate of 1.4%, how long will it take for the population to reach 15,300? Okay, so that's my equation there. So I know that the population is decreasing to 15,300, so my y value would be 15,300. The initial population is 20,000, so my a value would be 20,000. Now the b value always represents how much you're increasing or decreasing by. When you're working with percent, if you're increasing, you'll add to 100%, because 100% would be, if you're 100% of something, that means it just stays the same. Okay? If you're decreasing, you'll subtract from 100%. So because we're decreasing, we're going to take 100% and subtract 1.4%. Okay, and then we'll type that in our calculator and we end up with 98.6%. Now, if you were to type this in your equation with 98.6 as your b value, you'd end up with a crazy big answer. So our b value always needs to be in decimal form. So we're going to just write that in decimal form, which is 0.986. All right, now we just solve for t. At this point, you could graph. We're going to solve it algebraically, but because it doesn't say solve algebraically, you could really do anything you wanted here. I'd probably solve both ways. For me, when I'm working with math, I always solve every question in more than one way if I can, just because then I can double check and make sure I did it right. So 15,300 divided by 20,000 is 0.765. 0.986 to the exponent of t. Now, because we're trying to solve an exponent, whenever we're trying to solve for an exponent, we use logarithms. So we're going to write log. Our base is 0.986. Our argument is 0.765. And it all equals that exponent of t. So now we'll type this in our calculator, and we should end up with approximately 19 years. Okay, so this is just a couple of quick little diploma review questions. I will explain them. I would suggest that you press pause. Okay, try them yourself, because this is a review on what we've done, and see how many you get right out of 4. Okay, so this first question, the equation m log b, we're going to write in exponential form. So the trick is there's different ways to do this question. The first thing I would do, though, no matter what, is I would subtract that 5 over, because you can't convert to an exponential form unless that logarithm is isolated, and right now that 5's in the way, so I need to move it over to isolate that logarithm. So now from here, I could divide the m over if I wanted. That's a possible answer. And then I could convert to exponential form. So my base would be p. My exponent would be q minus 5 over m, and it all equals my argument. But the trick is that's not one of the answers that's given. So this is a correct answer, but it doesn't match the solution here. So that means there must be another way that I could write this. So let's backtrack back to this step here. So instead of dividing that m over, we could also use our log laws and write that m, because it's a coefficient, as an exponent on our argument. Okay, and now I'll convert to exponential form. So my base is p, my exponent is q minus 5, and it all equals my argument, which is n to the m. All right, and that is an answer, which is answer B. Okay, next question. The expression 3 log x and 3 log x is equivalent to what? With all of these questions, because these are diploma questions, and trust me, you can do this on the diploma, is I would double check by substituting variables in and make sure the left side balances the right side. So what I mean by that is something like this, I would substitute a number in for x. So maybe I'd make x 25. And then I would try each solution and see which of those gives me the same answer. So that's how I'd verify. And that's why I love verifying. Okay, but we're going to do this algebraically using exponent laws and log laws. So sometimes kids throw their exponent laws out the window. we are multiplying two exponents with the same base. So even though that those exponents are logs, we can still use exponent laws. So when we multiply two exponents with the same base, we add the exponents. So log x plus log x is just 2 log x. However, that's not one of the answers. So now I use log laws. So I can move that coefficient to an exponent on the argument. And then my correct answer is A. All right, next question. We've actually already have done this one, I think, earlier. This is just log laws again. So whenever I'm using log laws, I'll always move the coefficients as exponents on the argument. Of course, when you divide by 2, that's the same as timesing by 1/2. So a lot of times for kids, when you rewrite it that way, it's easier. Okay, and now I'll just move that coefficient as an exponent on my argument. Okay, when you have a positive argument, it goes on the numerator. When you have a negative, it goes on the denominator. Remember, z 1/2 is the same as root z. Positive, the y to the third goes on the numerator. There we go, there's my answer. And again, this would be the type of question I'd double check by just substituting values in for x, y, and z, and then making sure this expression is equivalent to this expression. All right, last question. The equation of the asymptote for the graph is y equals log b x minus 3 plus 2. All right, where b is greater than 1. So remember, the first thing you have to remember is that logarithms have vertical asymptotes, right? So that vertical asymptote on, say, a normal log graph would look like this. There we go. So a normal log graph, and by a normal I mean log b to the x, okay, would have a vertical asymptote at x equals 0. So what's happening is you are moving your graph up 2. That's not going to change that vertical asymptote. It'll change your x-intercept, but it won't change the vertical asymptote. But you're also moving the graph to the right 3. So I move it 3 units to the right. Okay, so now my vertical asymptote will be at x equals 3. So the correct answer is C. Here are some questions for you to practice, and next lesson we'll look at some applications.